So here we have our simulated riverbed with our levee and full simulated stream. We have a rock bed to aid in the simulation just a little bit with a nice deep high velocity flow. And here you notice we have a hydraulic jump occurring with a supercritical flow coming down the backside. We'll talk more about that later. So here we have our subcritical flow with infiltration through our levee. That's why we still have some flow there. And now it's become supercritical with our hydraulic jump, which dissipates energy. And then also notice we have turbulent flow through the grass, which is part of the friction in our n number of our Manning's equation. This is a diagram of a hydrograph showing our before event of our river flooding. You notice that our peak flow rate is equal to the level capacity, or the capacity of our levee, and at no point exceeds it. Therefore, we remain in a stable state. And this is after our levee becomes topped. It's also a hydrograph, but our levee capacity is the same. This is showing when we get the excess runoff condition going over top of the levee. And the second line drawn down is our time of levee failure, showing just how much of the flow rate actually did run off.
Now we will talk about Manning's equation.
When Dad gave up $2 for his marriage license fee, he really had no idea what an athlete he'd be. To gain his reputation, Daddy did not have to roam.
Alright, so what we got here is our Q, which is our flow rate, and then 1.49 over N, which is our Manning's N number, which is what we're trying to find with this whole here equation. Then we have R to the 2/3 power, which is R squared, taking the cube root of that in case all y'all are new to mathematics. Now, R, as we look over here, is actually our area divided by our wet perimeter. So what we have is a rectangular flume with our three areas, and we add those together to get our perimeter divided by our overall area of the flume. And that gives us our R for right there. Now, we have our square root of S. S is the slope, which is our change in height over time, so obviously that changes. Now A, as we said over when we are finding our R, is actually just the area of our flume, and we need to multiply all those together, and that would give us our flow rate. But of course you can just separate any of these variables out and find whatever it is you're looking for, including your Manning's N. Critical flow is where we go from our stored potential energy of the weir to the kinetic energy of downslope. The supercritical flow is supercritical because it has both the kinetic energy of the flow and also the gravitational energy transitioning into kinetic energy from coming down the levee. Our critical jump is where that can't be sustained anymore, and it goes back to a subcritical flow, which is just what the natural flow would be should this all be level.